December 2018. Question number 5. The question states that an actual gas turbine power plant operating on an ideal Brayton cycle has a pressure ratio of 8. The gas temperature is 27 degrees Celsius at the compressor inlet and 1027 degrees Celsius at the turbine inlet. The isentropic efficiencies of the compressor and turbine are 80% and 85% respectively. Assume that the working fluid to be air throughout the cycle. Sketch the cycle on a TS diagram and determine the turbine actual exit temperature in Kelvin, the backwork ratio, the thermal efficiency of the cycle in percentage, and the new thermal efficiency of the cycle in percentage if a regenerator having an effectiveness of 90% is installed to heat up the air leaving the compressor, and briefly explain the changes. Given that constant specific heat capacity CP, CV, specific gas constant R, and specific heat ratio K. If we draw the TS diagram for this ideal Brayton cycle, it should be look like this, and we take state 1 as the state entering the compressor. Next, I would suggest for you to extract the informations given by this question. In this question, given for us, the first item will be the pressure ratio equal to 8, and then 27 degrees Celsius for the compressor inlet, which is referring to the temperature for the state 1, 1027 degrees Celsius for the turbine inlet, which if you refer to the TS diagram that we have drawn, it should be referring to the temperature for the state 3. Also given to us is the isentropic efficiencies for both compressors and also turbine. So the isentropic efficiency for the compressor is given by 80%, and isentropic efficiency for the turbine is given by 85%. Since the isentropic efficiencies is given to us, then we know that we can determine the actual properties for certain states, especially when it's leaving the compressor and the states that is leaving the turbine. Therefore, if we alter our TS diagram, it should be looked like this, where we now have the actual state leaving the compressor and also the actual states leaving the turbine. Next, let's have a look at the item requested by this question. So the first item requested is the turbine actual exit temperature in Kelvin. So in order for us to determine the turbine actual exit temperature, which is referring to the T for A, so we can determine the T for A by first we determine the value for the T for S by using the isentropic relation for the process 3 to 4, and then we can determine the value for T for A using the isentropic efficiency for the turbine, which has been given by this question. Next will be the backwork ratio, or in short we can call it as BWR, is given by power input divided with the power output. So both power input and power output, we can have the expression from the steady flow energy equation. Item C is to determine the thermal efficiency of the cycle in percentage. We know that thermal efficiency is given by the desired output divided with the required input. For gas power cycle, Brayton cycle, the thermal efficiency is equal to the power net output divided with the heat transfer rate input. So these two terms can be expressed from the steady flow energy equation. The last item, item D, requires us to determine the new thermal efficiency if, let's say, we have a new Brayton cycle with regenerator. So for this, we are going to compare later on with the ideal Brayton cycle that we have determined in item C. For gas power cycle, the aim is to find the temperature for each states for the cycle. This is due to, in order for us to determine the enthalpy for gases, we are going to use formula enthalpy equal to Cp times the temperature. Therefore, in order for us to determine the enthalpy for each states later, we need to know the temperature for every states for the cycle. Alright, now if we look to state 1, so T1 is equal to 27 degrees Celsius. This value has been given from the question. So please ensure that you convert degrees Celsius into the unit Kelvin. For state 2, we are going to determine the temperature at state T2S by using this isentropic relation, since the process from 1 to 2 across our compressor is in isentropic process. Thus, we are going to get the value for T2S will be equal to 543.42 Kelvin. Since we have the isentropic efficiency for the compressor, thus we can find the actual temperature for state 2, which leaving our compressor. Okay, so from the formula for the isentropic efficiency for the compressor, we can determine straight away the value for the temperature for the state 2A, which we are going to get. The value is equal to 604.28 Kelvin. For state 3, the temperature has been given by the question, and please do not forget to convert the degrees Celsius into unit Kelvin. For state 4, we are going to determine the temperature for state 4S by using the isentropic relationship for the process 3 to 4. Then we are going to determine the actual temperature at state 4 by using the isentropic efficiency for the turbine. Now let's have a look at item B requested by this question, which is the back work ratio BWR. It can be determined by using the formula of work input divided with the work output. So the work input and work output can be obtained by using the steady flow energy equation. So for the work input from the steady flow energy equation SFEE, we are going to get enthalpy outlet minus with the enthalpy inlet, which is referring across our compressor. So for that, we are going to get enthalpy for state 2A minus with enthalpy for the state 1. Since this will be the gas problems, then we are going to find the enthalpy by using the formula CPT. So we are going to just substitute with the formula. Therefore, we are going to get for the work input will be equal to Cp times T2A minus T1. Same goes to the work out. So the workout from SFE, we are going to get enthalpy in minus enthalpy out for the turbine. So will be enthalpy at state 3 minus with enthalpy at state 4a, and we know that for gas questions we are going to use the formula to determine the enthalpy. Alright, so then you should substitute all the necessary value. Then do not forget to times with 100%. So then we can get the value for the backwork ratio in terms of percentage. Okay, item C is for us to determine the thermal efficiency for the cycle. And like I've told you before, thermal efficiency is equal to the desired output divided with the required input. So for this Brayton cycle, the desired output will be the net work output, and the required input will be the heat transfer in. So the net work output is given by this expression, and the heat transfer in is given by this expression. These expressions can be obtained from the steady flow energy equation. Alright, next we are going to substitute all the necessary value, and then again please do not forget to times with 100% so that we can get the end value in terms of percentage. Thus, for this particular question, we are going to get the value for the thermal efficiency will be equal to 27.41%. Alright, so the last item requested by this question is item D, where they request us to determine the new thermal efficiency if, let's say, we have Brayton cycle with regeneration, and given to us is the regenerator effectiveness, which is equal to 90%. If, let's say, we want to draw the TS diagram for this Brayton cycle with regeneration, thus it will look like this, where we have state 5 over here. The 5 prime is the maximum temperature when the regeneration occurs, and the state 5 will be the actual temperature once the substance leaving the regenerator before entering the combustion chamber. Okay, now from the regenerator effectiveness that has been given to us, so we know that the effectiveness is equal with the Q regen divided with the Q regen max, and the Q regen is equal with Cp times with T5 minus T2a, and Q regen max will be equal to Cp times with T5 prime minus T2a, and we know that T5 prime is actually equal with T4a. Alright, so from this formula, we can determine the temperature at state 5. So for this question, we are going to get T5 equal to 784.96 Kelvin. And next, we are going to determine the new heat transfer in, since the heat transfer in for this Brayton cycle with regeneration occur during the process 5 to 3. So the heat transfer in, the new heat transfer in can be determined by using this expression Cp times with T3 minus T5, and then once we substitute and calculate, we are going to get the value for the new heat transfer in is equal to 517.62 kilojoule over kilogram. And now we can determine the new thermal efficiency for this Brayton cycle with regeneration. So if you substitute all the necessary values and you calculate, you are going to get the new thermal efficiency is equal to 37.02%. Alright, so now we have two values for the thermal efficiency. This value is for the simple Brayton cycle, and this thermal efficiency is referring to Brayton cycle with regeneration. From this question, you are required to compare these two values of the thermal efficiency for different Brayton cycle approach, and you need to make in terms of statement. You may write something like the thermal efficiency of the gas turbine has gone up from 27.41% to 37.02% as a result of installing a regenerator, or maybe you can say as a result of regeneration process implemented to the Brayton cycle.